afternoon, everyone. Welcome to our webinar. My name is Jan Thomas. I am the Training Program Manager for the Center for Technical Development, or CTD. And CTD exists to promote training opportunities and professional development for district staff in Washington, as well as partners. So I'm really happy today to be able to help bring this soil Data's webinar to you with Danny. I just want to give you a couple of quick logistics about the webinar today. When you are ready to ask questions, we'll be using the Q&A feature. So that's one of those little icons down at the bottom. It's a box with a question mark and a Q&A. That's how we'll ask questions today. The chat feature that you might be used to in a regular meeting setting is not going to work for you today. So please use the Q&A feature for your questions, and feel free to put those in at any time during our speakers' presentations. We'll be monitoring those and answering them as we can, and we'll have a dedicated Q&A at the end. We are recording this webinar, as we have recorded the other two in this series, and they are all will be posted on the CTD website as well as through the Soil Health Initiative channel. So look for those. And if you registered for any or all of these, you will get an email with all three links at the end of it as well. So you can get those recordings out to you. I think that's all I wanted to say. I might be forgetting something, but I'll hand it over to Danny, and then she'll pick up for me if I forgot something. So thanks a lot.
Yeah, thanks, Jan. Hi, everyone, and welcome to our final webinar in our 2025 Making Soils Data Actionable series. I'm Danny Gilardi, Senior Soil Scientist at WSDA, and I am excited to welcome you all here to talk about soils data. All month long, the Washington Soil Health Initiative has showcased projects across Washington that use soils data to make real-world on-farm decisions. We do this because we love soils data, and we also know that it can be confusing. More soil tests and data are available to farmers than ever, and while this can be empowering, it can be difficult to translate into action. So today you're all here to learn about using nitrogen credits in crop fertilizer budgets. A quick announcement, if you had to miss our last events, however, is that the recordings for the soil compaction and precision ag webinars are already available online. So let's get started with some introductions. Today you'll hear first from Dr. Rich Koenig, a soil scientist and extension specialist from Washington State University, who has spent the past 30 years working in dryland and irrigated cropping systems in the Western United States. Then at 12:40, Savannah will join us. She is a resource conservation planner at South Yakima Conservation District, where she works on nutrient and irrigation management. Savannah earned her Bachelor of Science in Animal and Natural Resource Sciences from Washington State University. So for everyone in the audience, as Jan said, there will be a Q&A at the end, so feel free to post your questions into the Q&A feature as we go. And Rich, thanks for being here today. Feel free to take it away.
All right. Thanks, Danny. Let me share my screen here. Looks like that should be coming through in presentation mode.
Yeah, looks good, Rich.
All right. Thanks for the invitation to speak to this group today. I really like the heading, Making Soils Data Actionable. So as Danny introduced me, I'm a soil scientist here at WSU, and I've worked across many different cropping systems in the West. And today I'm going to share my perspectives on some of the soil nitrogen credits that you encounter and probably work with on a day-to-day basis. And maybe starting with the what and the why. So we know that it's important to estimate or assess or quantify the contributions of nitrogen from soil and other sources. And we use those in our nitrogen budgeting process. And I'll just show you a quick example here in a few moments. And then we also know that crediting nitrogen is important both for economic reasons and environmental reasons. There's a real value associated with the nitrogen credit, and if we ignore that credit or those credits, there are a potential anyway for real environmental consequences. just want to roll through a series of nutrient management guides. If you go to any nutrient management guide for crops in the Pacific Northwest or anywhere in the US, there's some form of nitrogen crediting process embedded within those nutrient management guides. So to various extents, they'll credit nitrogen from soil, from additional sources like irrigation water, maybe historical or prior applications of manure and other things. So really common to use nitrogen credits and in the nitrogen budgeting system for a whole variety of crops. And I just rolled through dryland winter wheat, silage and grain corn, and then potatoes. So silage and grain corn being here. You can access these guides online. They're freely available. And again, wherever you're at, you would have access to similar nutrient management guides for crops that you work with. And in these guides, they follow a fairly standard process. So the credits are used to adjust the base nitrogen requirement for a particular crop. So the base nitrogen requirement is a function of the crop species and the yield potential in most cases. So you start out with that base requirement, and then you subtract the credits, the residual soil nitrogen, organic matter mineralization, and so on and so forth to calculate the net fertilizer nitrogen needed. So for this session, I've got a few goals. First, I want to review the origin of the soil nitrogen credits. So I'll specifically focus on the soil credits, give you some insights, maybe a little bit of background as to their origin, and then also a few of the limitations in trying to assess credits associated with soil and soil processes. Ultimately, my goal is to increase your comfort level in using these credits, and then encourage you to learn and develop your own interpretations. And I'll talk a little bit more about that as we go along. So I'm going to break credits into three major categories. I'll talk first about soil residual nitrogen, and then I'll talk about soil organic matter decomposition. I'm not going to go into prior legume crop manure and other credits, irrigation water. I'll stick with the soil credits. But I break these up into different categories because, as we'll see for soil residual nitrogen, that credit is based on a point in space and time, and we assess soil residual nitrogen by virtue of a soil test. The next group, the next three, organic matter, legumes, and manure, are based also on point data. What is the current soil organic matter level, or how much manure was applied, or what's the legume crop residue addition? But then they're also based on a forecast or a projection into the future as to what's going to happen with that material. How quickly is it going to decompose and mineralize or release nitrogen? And then irrigation water, again, based on a sort of point sample in time. When we talk about soil residual nitrogen, the basis for that is that we can quantify the concentration or levels of plant available nitrogen in a soil sample at the time we take that sample. And those forms of nitrogen, as I'm sure you all know, are nitrate, the anion form, and ammonium. So these are the two forms that are commonly accessed or taken up by plants, and there are relatively simple ways to measure the concentrations of those two forms of nitrogen in soil. But one thing to be aware of is when we measure soil residual nitrogen, it's a point sample both in time, so it's good as of the day we collected that sample, and in space. And it has some limitations in terms of interpreting soil residual nitrogen or soil test nitrogen for those reasons. You all know that spatial variability is a big consideration in collecting soil samples in the field. In the upper right, this is an image of the Palouse, the rolling hills or topography of the Palouse. Lots of spatial variability in the Palouse associated with landscape position, processes that occur in the soil, crop yields. Everything is spatially variable or dependent in the Palouse. And then in the lower left, image of a field more typical of the Columbia Basin, flat topography, maybe a little less spatial variability, although not always the case. But spatial variability is something that we deal with every day when we try to go out and collect a soil sample that's representative of the field. So that spatial variability challenge. And again, to sort of remind you of the magnitude of the challenge, if we were to collect and weigh soil spanning an acre to a depth of 1 foot, there's about 4 million pounds of soil in that acre foot. And that's only 1 acre. When you collect a soil sample, often are submitting only a pound of soil, maybe a little more, maybe a little less, to the lab for analysis. And then the lab's analyzing a much smaller fraction, usually somewhere between 1 gram to maybe up to 5 grams of soil that's analyzed by the lab for soil available nitrogen, nitrate, and ammonium. That's assuming that the sample represents 1 acre. Most samples represent much more than that. So the challenge is to collect a sample that's representative of that field or that acre or area that's sampled and get that to the lab where they'll conduct the analysis. Just to give you some quick percentages, if you take an acre and sample that based on 4 million pounds of soil per acre foot, you're submitting a very small fraction, very small percentage of that soil representing that acre to the lab, and they're running a much smaller percentage of that in their analytical process. So we point to various soil sampling guides, smart sampling. There are many different techniques that have been developed to try to aid you or guide you in collecting a representative soil sample. And this is where some knowledge of the field, the history of the field, or some of the variability in crop yields and soil properties, soil type is really important to guide your sampling scheme. And then once you collect that sample, Washington State is very fortunate. In fact, the Pacific Northwest in general, very fortunate to be supported by many testing labs that support or run samples for commercial agriculture, for research, and for individual private homeowners and so on. So I'm going to highlight a few of those testing reports and then point out some of the features and how the lab works with the sample and the numbers that they obtain in the analytical process. I've redacted the contact information and some of the other information on these samples, so they've been anonymized. So this is a testing report from Quo Testing Labs, and if you look across the top, it contains the nutrients that Quo tested the samples for. There are 3 samples here identified as strong, weak, and weak replant. They're all from the 0 to 12-inch depth, so the top foot here is indicated on the far left. And you'll see for nitrate nitrogen, one of our plant available forms of nitrogen, there are 2 numbers listed there. One is a ppm, a concentration in ppm. ppm is a unit that sometimes I think was created to confuse students, academics, and the industry. It's a concentration in parts per million. ppm stands for parts per million. You can equate that to pounds of nitrate nitrogen per million pounds of soil. So it's simply a concentration of nitrogen, if you will, in that soil that the lab has expressed in pounds per million pounds of soil. So where that becomes important is if we take that part per million number, and we know that at, let's say, an average bulk density of about 1.4, 1.47 grams per cubic centimeter, there are about 4 million pounds of soil in an acre foot. So what that means is if we have a concentration in parts per million or pounds per million pounds of soil, we can multiply that concentration by 4, the number of million pounds of soil in that acre foot, to scale up or convert that concentration from parts per million to pounds of nitrate nitrogen per acre. So this is a common calculation that's done. Often test reports will present nitrate and ammonium concentrations in parts per million, but also in pounds per acre. But important to know how how that amount, pounds per acre, is calculated into the future. And then many of the testing labs also offer some really nice dashboards that give you an interpretation of the soil test results, not just for nitrogen, but for other nutrients as well. So dashboards, recommendations for a particular crop situation. So again, really nice support features from testing labs in the state of Washington and in the Pacific Northwest as well. But I'd just make a plug for learning a little more about how those soil tests are interpreted. So spending a little bit of time brushing up on your own interpretation or your own information, if you will, so that you're able to interpret those soil tests yourself. You can start with this excellent guide from Oregon State University. It's a general soil test interpretation guide. And then some of the crop nutrient management guides that I referred to earlier, they also help or aid in interpreting soil test results. And then I would be remiss, the earlier reports that I showed were for samples collected from the top foot of soil. But as you know, we can go deeper, and it's often informative to collect a soil profile, a collection of samples in 1 foot increments from the surface down as deep as you're willing or able to go. So in the dryland areas of eastern Washington, the rain-fed areas, we often go to 4 feet, 5 feet, 6 feet. We know that spring wheat and winter wheat are capable of rooting to those depths. And it's really fascinating and interesting to see what shows up in the subsurface, in particular when it comes to mobile nutrients like nitrate, sulfate or sulfur, and chloride. And then also really important in the dryland areas is where's the water, where's the plant available moisture, and how much is there, because that's a big driver for yield. So deeper sampling is a possibility, and in fact, I would say encouraged to try to assess plant available nitrogen in the plant root zone or the crop root zone, but also maybe trying to figure out or see what's going on even below the root zone for the plant. Here's another report, again, similar set of data here, profile down to 6 feet. And then this is one I often use in my soil fertility class as a challenge to the students to tell me what's wrong with this situation, or to see if they can diagnose what created this situation of ultra high nitrogen levels in the soil profile. High pH, if you look across here, a pH of 8.5 and other characteristics. So you can find out or learn a lot about a full profile analysis like this. I'll say this incidentally came from a sub-irrigated flat in the Palouse, where a lot of the surrounding slopes and hillsides, water and things that are in soil water end up showing up in the flat, the sub-irrigated flat. So I'm going to move on now to the next soil nitrogen credit, and that's soil organic matter decomposition or mineralization. And again, just a couple of words about this credit. So when we talk about soil organic matter decomposition or mineralization of nitrogen while organic matter decomposes, what we're referring to is the portion of long-term resident organic matter that we know decomposes each year in the soil and releases nitrogen in that process. So what we're talking about is this, the dark colored humic material, the organic matter that's been in that soil profile for decades or maybe perhaps even centuries. So we know that this material turns over, a small fraction decomposes each year, but we want to differentiate this from the fresh residue, which we account for in other parts of our nitrogen budget, our credit or debit system. So we're really talking about, again, the long-term resident soil organic matter and trying to assess how much of that decomposes and releases nitrogen in any given year. Decomposition is a biological process. So not only are we interested in measuring the amount of organic matter in soil through a soil test, but we're also trying to predict the rate of decomposition and release of nitrogen from that organic matter. So some additional details here for this credit. I call it both a point sample in space, reflecting the fact that you're collecting a soil sample, and that's the means by which you determine soil organic matter composition or percent. But then also you're making a prediction over time, how much of that organic matter is going to decompose and how much nitrogen will be released over time in a particular cropping system. Like with a soil test nitrogen, a residual nitrogen, we've got a point in time in which we're collecting a soil sample to determine organic matter content. That point is subject to spatial variability and trends, much like residual nitrogen. So trying to collect a representative sample from the field is really difficult sometimes, but critically important. One of the big differences between, let's say, nitrate and ammonium and organic matter is that while they're both spatially variable, organic matter is much more stable over time. So if you collect a sample from a site that's high in organic matter, it's likely to remain high in organic matter over reasonable time frames anyway. So it's less subject to temporal variability than nitrate and ammonium. And then again, the other issue, if you will, or consideration when we're predicting or projecting nitrogen release from organic matter is what's the rate of decomposition of that organic matter. And we know that because it's a biological process, that temperature, moisture, aeration, or oxygen are really the main drivers. And we also know that these can vary over space and time as well. So if we go back to our example soil test report, this is one that I showed earlier. We find a column on this report for organic matter. I think all of the labs that do routine soil analysis run organic matter and present that usually in the top foot or 12 inches of soil as it's done here. And then if I had provided more information to Northwest Ag consultants, they would have calculated an estimate of nitrogen release from organic matter and even a nitrogen recommendation for a particular cropping situation. This was for a research trial location though, so I didn't give them full information necessary to run the final calculations. So how do we get from percent organic matter in the soil, though, to our estimate of how much nitrogen is going to be released by that soil? So what's the factor, if you will, or the conversion? If we go to another soil test report, this one from Soil Test Farm Consultants, I showed this one before. Up here, we've got organic matter content in this soil, 3.3%. It's also a soil sample from the surface or top foot. And this lab has calculated ENR, estimated nitrogen release, at 66 pounds of N per acre. So what this lab is using is a factor of 20 that for each percent organic matter in the soil sample, there's an estimate of 20 pounds of nitrogen released. So you multiply the percent organic matter 3.3 times 20 and come up with the 66 pounds of nitrogen. That's the estimated and release from organic matter. That number 20 is common. So when you look across a range of nutrient management guides, you'll see 20 pounds of nitrogen per percent organic matter show up in some of those guides. Under irrigated situations like this one from irrigated potato production in central Washington, the range is 25 to 50 pounds of N per percent organic matter. 17 to 20 in dryland area. No credit for that silage and field corn guide written primarily by authors from southern Idaho. They note in that guide that there isn't a good relationship between soil organic matter content and N release in those systems. But again, quite common to see values cited and referenced in those guides. Wanted to spend just a couple of minutes showing you some data from a study that was done a number of years ago now by a graduate student at WSU named Tim Fees. He went into the Palouse landscapes, or spatially variable Palouse landscape, and he did a number of things in this research, but one of the things he did was to estimate nitrogen mineralization across the landscape. So at different locations in the landscape, from the foot slope, the base of the slope, the north back slope, the south back slope, so north and south aspect, and then shoulder near the top of a Palouse hill. He did this over 2 years and at a couple of different locations. And what he found was that the overall average rate of release of nitrogen from organic matter was 27 pounds of N for each percent organic matter in those soils. So that was the average. There was some temporal variability overall, 23 pounds of N per percent organic matter released in year 1 of the study, 31 in year 2. So a little bit of year-to-year variation, which you might expect based on differences in weather patterns from year to year. And then across the landscape, quite a range from 22 to 40 pounds of N per percent organic matter released in different landscape positions. So there was a landscape effect or a spatial effect as well as a temporal effect. So again, expect that there will be some variation from year to year and in different parts of a field or of the landscape in terms of how much nitrogen is released from organic matter as it decomposes. And I wanted to come back to maybe another way to look at this. If we throw it back into a soil organic matter nitrogen credit, we can do this as a mathematical exercise. If we assume that soil contains 2% organic matter in the top foot, we go back to our 4 million pounds of soil per acre foot. 2% of that by weight is about 80,000 pounds of organic matter. We know that the soil organic matter, this long-term stable material in soil, contains about 50% carbon and about 5% nitrogen by weight. So if you take 5% of 80,000 pounds of organic matter, that's 4,000 pounds of nitrogen. And then if we assume a 1% annual decomposition rate of that organic matter, that equates to about 40 pounds of nitrogen released from that soil each year. That soil that has 2% organic matter. Or if we convert that into nitrogen released per percent organic matter, we take 40 divided by 2% organic matter, and that's 20 pounds of nitrogen released per percent organic matter. So we get back to that number used in that prior soil test report. And research has shown, yeah, it varies widely place to place, different environments or climates, but somewhere between 1 to 3% of soil organic matter decomposes annually. That's a reasonable range across different systems. So that would be equivalent to somewhere between 20 and 60 pounds of nitrogen per percent organic matter as a soil organic matter credit. So a couple of final words or perspectives on the soil organic matter nitrogen mineralization credit. That 20 pounds of N per percent organic matter, that's probably a reasonable number, but it's likely to be conservative. And it, in particular, may underestimate release in irrigated systems or high disturbance systems where we've got more water coupled with higher temperatures during the growing season. They tend to trigger or promote more mineralization and release. And then high disturbance systems that mix up the soil and bring more organic matter in contact with organisms will tend to promote release as well. That estimate's also based on organic matter in the top foot of soil, and we know that there's some organic matter below the top foot. Yep, the concentration or percentage goes down, but there is some there, and it's likely releasing some nitrogen as well. But what I say here at the end is that I think that's okay because cropping systems are resilient, they're buffered. Conditions that increase or decrease organic matter decomposition, so seasonal conditions or tillage or other things that we might impose or do to the soil, those conditions also affect the crop in similar ways. So in years where we see more organic matter decomposition and release of nitrogen, we tend to see better crop performance because the weather conditions are more conducive to crop growth. So there's a bit of insurance built in, again, resiliency built into the system that if the plant needs more nitrogen, it may be released by that organic pool. If it needs less because of some restrictions on growth due to weather, the soil itself may actually release less nitrogen due to those same conditions. Okay, to just recap, so I started out with my goals for this session to review the origin of the soil nitrogen credit. So didn't get into some of the other credits associated with manure or crop residues, legume and non-legume, and irrigation water. Those would take an additional time and maybe be the subject of a separate presentation. But the focus here was on soil N credits. And again, the goal was to hopefully increase your level of comfort in using these credits, understanding the origin of the credits, and then also to encourage you to develop your own interpretation. So go out, look at the extension publication, some of the research literature. You know more than the testing lab about the field conditions, the management situation that you're dealing with. So would really encourage you to tool up, if you will, and be able to develop your own interpretations from soil test reports for the soil N contributions. So with that, I want to thank you for your attention, and I'm going to pass the torch now to Savannah, and I will be here during the Q&A session, so I'll be happy to take any questions you have at that time.
Okay, I think I'm screen sharing now. I just want to make sure everything's good.
Yeah, it looks good, Savannah. It's not full presentation. Ah, there you go. You're ready to go.
Okay, so as Danny mentioned earlier, my name is Savannah. I am a resource conservation planner here at South Yakima Conservation District. I've been here for about 2.5 years now. We're located in Zillah, Washington, so it's considered like the lower Yakima Valley. South Yakima Conservation District essentially covers the lower half of Yakima County. So I figured I'd get started talking about our deep soil sampling program here at the district. So we've had the program. It's generally a pretty new program. We've had it in full force, I think, just started this fall. But we did do a pilot project a few years back, and we also had this program from about 2014 through 2016. But we've decided to get it started up again. This is a free program for our landowners within our district boundary. We take soil samples in 1-foot increments, and our goal is to make it down to 6 feet if possible. Sometimes soil conditions won't let us get that far, depending on the type of drill that we're using or the bit that we're using. Sometimes it's too far compacted, or sometimes you're hitting gravel layers or rock layers and you just can't get as far as 6 feet, but we try to get down there if we can. And this is part of our nutrient assessment and planning program here. We have a really long acronym. It's called LIVNAP, which stands for Lower Yakima Valley Nutrient Assessment and Planning Program. But it also comes kind of hand in hand with irrigation water management too. The photo that you see on the right is an example of a soil tube. Soils collected in these tubes, they're about, I think, just under 2 inches in diameter. And each tube is about 3 feet long. So we'll collect 2 tubes to get down to 6 feet. But that's just an example of a soil tube with some soil that was collected. Okay, so this is our deep soil sampling drill. The our oldest one. We actually just got a new one, but that'll come later. It's a Bobcat UV34 UTV, and then mounted on the back is a Giddings rotary drill. It's a hydraulic powered rotary drill, so it essentially just spins around as it bores its way down. And then you just pull it up and the sample should be collected in tubes. The photo here is a picture of Rodney Height. He's the manager here at South Yakima Conservation District. The program's goals are to ultimately assist landowners. We're trying to assist with nutrient management and provide a benchmark condition of what is in the soil. We've worked with some landowners that actively soil sample, but they don't usually sample down to 6 feet or even past like 2 feet or 3 feet. And we work with some landowners that have never sampled before, and they farmed their land for, 30 years, or it's just been a long time since they've sampled. So it's good to give them a benchmark condition of what exists at that moment in time. Our goal is to help reduce nitrogen leaching, specifically nitrate, since it's the most mobile form of nitrogen. And it's the most mobile of most of the major nutrients that growers are going to be looking at in their soil. And we're also trying to reduce nutrient runoff, say from like over irrigation, or if it's like a rill or furrow irrigation system, and ultimately conserve resources for folks that are using commercial fertilizer as their fertilizer method. If they are over applying and find out that they're over applying, there's an incentive to save a little bit of money on commercial fertilizer since it's so expensive. So here we're looking at the analytes, what we're testing for. We test for nitrate, ammonium, potassium oxide, which is just the form of potassium, diphosphorus, pentoxide, and total carbon, and then also pH. So on the top foot, we're testing for all of those analytes, and then the 1 to 2 foot sample is going to be just the nitrate, P and K, and then from 2 to 3 feet, 3 to 4 feet, 4 to 5 feet, and 5 to 6 feet, we're just looking for nitrate. So how does our program work? We work with the landowner and we try to choose a representative location in their field. We'll look at like the soil types that exist in that field by using like Web Soil Survey, or the Soil Web app works really well on your phone. Basically, it's like a form of Web Soil Survey. If you aren't familiar with that app, it's great. So we kind of base the location on the soil type of their field. The dominant soil type usually is what we try to go with. We try to not take a sample in like a gully, a low spot, field edges, anything like that that could maybe skew results. We try to stay away from those areas. If a landowner says, hey, my field looks great, except I have this one spot in my field that I just can't get it to grow. It doesn't want to come in very well. We can go and take a sample in that location. But usually, generally speaking, we try to keep it representative of the entire field. We will take 4 bore holes 20 feet apart. So essentially, you create a location within the field, and from that location, 10 feet on either side is going to be 2 boreholes, and then 20 feet from those will be the other 2 boreholes. So it forms like a straight line within a circle, kind of. So it's like a whole like 60-foot diameter circle. And like I mentioned earlier, the soil is collected in 3-foot tubes. So we'll ideally, if we can get down to 6 feet or anywhere past 3 feet, we're going to be taking 2 soil tubes to get for each borehole. And each of those samples, each of those foot increments are composited together in like foot increments. So all the 0 to 1 foot, they're all going to be together in a bucket, mixed together. And then that is going to be backed up and sent to the lab. What's great about the program is it gives landowners some opportunities for further assistance from us. Not only are they figuring out, what is on their land, like what's in their soil, but they have an opportunity to get some assistance from us for things like nutrient management and irrigation water management. I just wanted to highlight this really quick is to the right is a soil moisture monitoring probe. It's a Centec drill and drop Bluetooth probe. They come in multiple different sizes, but we have, I want to say like 30 here at the district right now, 30 or 40, and they're 3 feet long, and they have, I think, I want to say like at least 10 sensors along like every 4 inches. I don't know, do the math on that. But they will monitor the soil moisture at different depths in the field. And then we can also help with putting together an irrigation schedule or irrigation water management plan based on like their field conditions, their soil, their cropping. And same with nutrient management. Or we might say, hey, we've got some agronomists that you might want to reach out to that can give you really good recommendations on like cropping and fertilizer management. And so finally, I wanted to share that we do have a brand new deep soil sampling machine. It just arrived, I think, last week or the week before. It's also a Bobcat UV34 UTV, but instead it has an AMS 9110 ag probe. And the difference between this one and our other probe is this one is a hydraulic hammer probe. So instead of spinning in a circle as it bores down, it basically goes and then collects the soil as it hammers its way down. So we're thinking that this is going to work a lot better in tighter silts or even kind of getting past some like little gravel layers. If they're finer gravels, it can go a lot faster than our other drill. So that's really exciting. And that's all I have. This is actually a picture out at the WSU Prosser, the IREC, the Irrigated Ag Research and Extension Center. We were doing some deep soil sampling for an ecology pilot project.
Thanks so much, Savannah and Rich, both of you guys, for your presentations today. It's really nice to hear from experts, just sort of simple, practical, actionable ways to action on soils data. We have a lot of questions coming in, and I definitely recommend people read the Q&A chat because Rich has been typing away, answering folks' questions. Thank you, Dr. Koenig, for that. So if anyone has more questions, please keep them coming. And in the meantime, we will start with one that I think ties your guys' presentations together really well. So when you're sampling soils for residual nitrogen, how deep is deep enough? And maybe Rich will start with you and then pass it over to Savannah.
Sure. Good question, Danny. Typically, we think about the depth of rooting for the particular crop that we're trying to assess the credit for. So sampling to the right depth would be what is the rooting depth of, if it's dryland wheat versus irrigated potatoes or silage or grain corn or vegetables. So that gives us a good start, if you will, in terms of estimating the credit that might go into our nitrogen budget for that crop. I also like to go a little deeper, if possible, and find out what's going on below the root zone of the crop. Sometimes that tells you a bit about past nitrogen management practices. Do I find nitrogen below the root zone, or is the root zone or the soil below the root zone, relatively low in residual N? So, first answer, be guided by the rooting depth of the crop, but don't be afraid to go a little deeper just for your own information. Usually the cost is minimal to go with the full profile as opposed to maybe just 2 or 3 feet.
So for both of you guys, when you're finding high levels of nitrate, in the 4 foot, 5 foot, 6 foot zone, much beyond the rooting depth of some crops, what do you tell growers about that? Is that an indication that, will that ever become available to plants, way down at 6 feet, or is it an indication of past over fertilization or future groundwater contamination? How do you interpret those deep results?
Rich, do you want to go or do you want me to talk?
Go ahead, you lead on this one and then I'll follow up.
So, yeah, it can really kind of depend. You know, we've seen some that it's been farmed by one person, they apply it, you know, what it was recommended at like a co-op that they go to buy their fertilizer. They say, hey, you know, generally apply it this many pounds per acre. You'll want to do it this time of year under these conditions. And sometimes you don't really find anything down at 6 feet or 5 or 4 feet. And then other times we kind of do. And it could kind of be based off of even like what irrigation system that they had previously. We've had some people that have switched from like a real irrigation system over to like a sprinkler system, a wheel line, or a pivot. So maybe previously they, because of the real furrow irrigation system, they had to drive water all the way down the rows, but in doing so, some was leaching down past the root zone, so that could have been the issue. But I've also seen, you know, some fields that have been in sprinkler for, you know, really long time, over 20 years or more, that have really very, very careful nutrient and irrigation water management at play. And one of the soils just happens to be kind of a subby soil that no matter what they do, they just can't get rid of the nitrogen. I've seen that in some places, and they say we have not applied to this field in over 15 years. And there it is at, you know, 3 feet down and you're seeing it, but in the top, you know, few feet, you're just not seeing it as much. So I don't know. Those are my thoughts. Did you have anything, Rich?
Yeah, so I like to use it, Danny, as an opportunity maybe to talk a bit about one, the value of the nitrogen that's in the profile. So, you know, I'll go back to an example with some of the dryland farmers. If, you know, if we've got 250 pounds of nitrogen per acre as nitrate and ammonium in a 5-foot profile, that's, you know, you can equate that to real value. And in a time like we're in now where fertilizer prices are high and crop prices are not, it's a good time to be thinking about, you know, drawing money from that bank, from that soil bank. So I think it's a good, you know, it's a good opportunity for discussion. And, you know, even if that nitrogen is below the root zone of the crop, it still is an opportunity to say, well, what's my rotation? And am I going to grow something after, you know, potatoes or vegetables that might be able to take advantage of that deep nitrogen? Or maybe there's a cover crop in between, an opportunity to recover some of that nitrogen. And then, you know, thirdly, it does, you know, it's a good indicator of nitrogen balance and that, you know, either because of application or maybe management of irrigation water, soil texture coupled with irrigation water management, some of that nitrogen, you know, escaped below the root zone. So how do I try to address that, learn and address that in the future? So we talk about, well, you know, just general nitrogen management and improving those management practices.
Thanks. That is a really nice tee up for the next question, which, you know, I think nitrogen management strategies are often really just risk management strategies. How can I put down enough nitrogen to ensure optimal crop yield? And so to mitigate risk, some growers may be tempted to apply more nitrogen than they need, even if they know that there are nitrogen credits in the soil they could use to reduce fertilizer use. So what do you tell growers to alleviate the kind of risk concern or you know, nutrient deficiency anxiety to get them to apply less or more accurate along the 4 R's that you showed, Savannah?
It's a really good question. Gosh, Rich, do you want to take this one first? I can maybe tag team along it, but that's a lot to think about.
So one of the things that I guess is really impressive about the industry is the technology that's available, particularly in irrigated systems, to assess the crop. So, that same testing labs that I mentioned that serve agriculture for soil analysis also serve plant or conduct plant analyses, and most of them are, really rapid turnaround. So, the combination of trying to assess what's in the soil, and then as you go throughout the growing season, continue to monitor the crop visually. A good field or crop consultant can identify deficiency symptoms, not just for nitrogen, but other nutrients visually, and then, take plant samples, have those analyzed, and you can make adjustments in season. And I think that's really a valuable strategy to optimize the crop and the nutrient needs for that crop. Dryland or rain fed, it's much more difficult because, if you need to make an application, you need moisture, rain to move that nitrogen or other nutrient into the soil and root zone. So much more challenging to maybe make adjustments if you need to in a dryland or rain fed situation. But lots of tools, lots of techniques through irrigation systems to inject nutrients and to make corrective additions if you need to. So.
Savannah, I have a question for you, and you touched on this a little bit right at the end, but can you describe the funding or technical support available for growers to improve their soil nutrient or irrigation management? And you can talk specifically about those resources at South Yakima or broadly at the conservation districts across Washington.
Yeah, so I know conservation districts operate under different grants, and a lot of our funding does come from the Washington State Conservation Commission. Through them, we have some different funding pools that can offer cost share for landowners to implement applicable best management practices. So it kind of depends, and sometimes it's not enough to cover a really big project, like if someone wants to put in several pivots or something like that, we may not have the funding for it. But I know Natural Resource Conservation Service, or NRCS, they often have a bit more funding than we do, to say the least. And they're often able to help landowners in that situation. But I will say we can also help with nutrient management or getting people in contact with the right people or some folks that might be able to supplement the landowner's knowledge. So did that kind of answer your question? I hope it did.
Yeah, that's perfect. You might be getting a lot of calls from folks in the audience for resources going forward. So there is a lot of pressure on growers to reduce fertilizer use and nitrogen use efficiency, to reduce nitrogen leaching and volatilization. So as practitioners in the field who are working with growers pretty closely, do you guys have any perspectives on regulatory versus voluntary approaches, and what do you see as being successful in that space?
I know from the conservation district standpoint, conservation districts evolve to be voluntary and non-regulatory. So that's the sort of assistance that we provide landowners. I do believe that obviously regulations, there is a need for regulations as well. We wouldn't be a society without some regulations. But I think a lot of landowners are willing to work under a voluntary approach. And I feel like they get more out of it as well because they can learn from the situation and kind of feel like they're doing their part in, conserving natural resources.
I might add, so I'm always an advocate for voluntary and incentive-based approaches, and I would also maybe go beyond that and say a real advocate for incentivizing an outcome not the pathway or the method used to achieve the outcome. So, if our goal is to improve nitrogen use efficiency or to improve a nitrogen balance, the input-output balance, state that as a goal, that's the outcome, but give producers and consultants the freedom to find their own path to that goal. When we sort of incentivize a particular practice without understanding how it might be, applied or misapplied, I think we stifle innovation and the ability to find, new and creative ways to meet a goal. So set the outcome, set the goal, and incentivize people to reach that goal by whatever means, creative means they have to do so.
That's really well said. One area that we struggle with is that our ultimate outcome we want to see is, of course, reduce nitrate in the groundwater. And that is really hard to measure, and it changes slowly. So even if everybody stopped applying nitrogen today, we may still see elevated nitrate in certain basins in 2 years. So Rich, what is your favorite way to measure or use a proxy for reduced nitrogen pollution? Do you have any experience with that?
Yeah, and so Danny, maybe a couple of approaches. One that I really like because it doesn't require intensive, detailed, frequent, sampling and monitoring of the plant and of the soil is a simple input-output balance. So if I know that I'm harvesting off or removing 100 pounds of nitrogen, and you can estimate that pretty easily with crop yield and rough estimates of the percent nitrogen in that harvested or removed portion of the crop. So if I'm removing 100 pounds and I'm applying 120 pounds, that by any measure, that's a pretty good input-output balance. Yep, you're applying 20 pounds more than you're removing, but that's better than applying 200 pounds and removing 100 pounds. And so that simple input-output balance is a good measure of sort of overall nitrogen system performance. And then the other thought is maybe be a little less hung up on reaching the number, whatever the established number is, but making progress in the right direction is important. So if I start at 200% nitrogen applied relative to what's removed, if I can bring that down to 150%, that's great. That's huge progress. Maybe I don't achieve 120%, but I'm moving in the right direction. And over time, we just want to move in that right direction and ultimately move towards the goal.
Thanks so much. So we have just a few minutes left. I hope I can get in 2 questions. We'll see. We had some questions in the chat, Rich, that you already answered, sort of about technology in the future. And during your presentation, you provided really simple strategies and math for measuring soil N credits. What do you think about new AI-driven trends and technological trends and sensors? How do these methods compare? And do you think sensors could one day replace a standard laboratory analysis?
Yeah, I just in my career, it's been amazing to see the technology, the sensors, the advancements in just the hardware side of things in terms of being able to interrogate the soil or ask questions in sort of real time and in real space. I don't know that we're there yet for something like nitrate and ammonium to be able to go and place sensors that will give us management grade information yet. And we still have the issue of spatial variability and some of the challenges that that we have to address or overcome. But I think we're on the cusp of that. I think we're going to see new rapid sensors that will be like a soil moisture sensor. They're going to be they continue to improve. We're going to see better sensors and maybe better opportunities to use them in the near future.
Okay, so last question, and we'll start with Savannah. What are you guys most excited about in agricultural trends today? What are you looking forward to learning more about or using more, or what are you hearing from your growers?
That's a good question. I think just the overall push towards more sustainable agriculture in general. I think it's just overall exciting to see landowners that are installing these best management practices, implementing them with or without our assistance, just because they know that they're proven, they work, and they will help not only conserve natural resources for everyone, but also themselves. They'll help save water, they'll help conserve their soil health and everything. So I'm also, I think, pretty excited to learn more and more about soil moisture monitoring. There's more probes that are kind of coming out. We were kind of experimenting with one here from an outfit out in the Midwest, and seeing if that might be another option as a probe that we might want to carry here. But just kind of learning about all those different support tools that could help landowners and make things a little bit easier, give them information in real time.
And I guess I would go back to your prior question. I think the most exciting thing is just the pace and what's coming in terms of technology and AI decision support, but also just the equipment, sensors, whole host of things that are coming to agriculture now from some of the other industries that have been benefiting from them.
Well, thank you so much, Dr. Koenig and Savannah, for your presentations today, and thanks to everyone in the audience for your time and attention. I hope to see you all in March 2026 for next year's Making Soils Data Actionable series. And in the meantime, you can find today's recording on the Washington Soil Health Initiative and the Center for Technical Development websites soon. So yeah, it was another great webinar series in 2025. Thanks, everyone, and thanks again to Savannah and Rich.